All right, let's just jump right in. Have you ever actually stopped to think about what happens the exact moment you hit enter on a command or ask an AI to write a script for you? We are literally bridging two completely different universes here. On one side, you have the associative, free-flowing world of human thought, and on the other, the strictly deterministic, physically rigid world of silicon processors. In this explainer, we're going to unpack exactly how that translation happens, the physical bottlenecks we slam into along the way, and why the future of AI completely depends on how well we master this exact divide.
So here's our roadmap. We'll start with the semantic bridge, move into the von Neumann bottleneck, dive deep into imperative programming, that's the step-by-step how, we'll weigh expressiveness against execution speed, and finally wrap up with the compiled AI solution.
Okay, Section 1, the semantic bridge. Let's look at the gap between our brains and the silicon. The biggest conceptual mistake we make is assuming computers process symbols the way we do. Trust me, they absolutely do not. Human text is incredibly fluid and forgiving, but down at the hardware level, there's no meaning. There are no actual ones and zeros sitting inside the machine. A data bus only understands physical realities, clocked voltage levels, switch states, and electrical charges. To get from a fuzzy human thought down to those literal voltage levels, we need a really precise semiotic bridge. And that bridge is the rigid, unforgiving syntax of programming languages.
Which brings us to Section 2, the von Neumann bottleneck. Now we're zooming down to the physical hardware itself.
So back in the 1940s, John von Neumann conceptualized this stored program architecture, and it's what almost every processor has used for the last 60 years. The defining feature here is that it physically separates the instructions from the data. The memory and the computing units sit apart from each other, connected by a shared bus. Now, for general-purpose computing, this is fantastic. It's incredibly flexible. But as we're about to see, this separation comes with a massive structural consequence.
Because memory and compute are physically separated, data movement in a von Neumann system is huge. To put it simply, our processors spend a ton of time just twiddling their thumbs, operating way below their actual capacity, waiting for data to be shuttled back and forth across that bus. We call this memory wall latency, or the von Neumann bottleneck. And when you're talking about modern AI, where we are constantly shuffling terabytes of static model weights around, this architectural quirk becomes a brutal physical constraint.
Moving on to Section 3, imperative, the step-by-step how. This is where we see exactly how software adapts to that hardware constraint.
Imperative programming is deeply, fundamentally tied to that von Neumann architecture we just talked about. Writing imperative code, like C or Java, isn't just typing text on a screen. You are dictating exact, step-by-step memory and state changes. Because the CPU sequentially executes commands that physically alter hardware states across the bus, the programming language itself is designed to mirror that physical process. You are explicitly telling the machine how to operate, fetch this piece of data, run this specific loop, modify this exact memory state, and write it back. We completely throw out the conversational ease of natural language in favor of bit-perfect execution that controls the physical state of the hardware.
But not everyone loved this. Listen to this absolutely scathing critique from John Backus. He literally led the team that created Fortran, the quintessential imperative language. But in his 1977 Turing Award lecture, he called these von Neumann-style languages fat and weak. Why? Because relying on this low-level, step-by-step stateful computation, constantly updating memory values like you're rigidly following a baking recipe, severely limits our ability to build clean, mathematical, algebraic structures. The physical reality of the machine forced a programming style that is incredibly strict.
Section 4, expressiveness versus execution speed. Every structural choice has a cost, right?
Let's look at a really simple problem, checking if a number is in a list. On the left, we have functional code like Haskell. It's stateless, it's recursive, it expresses the mathematical logic of what to compute. But over on the right, we have imperative code like Java. Java demands exact, step-by-step control over how the machine iterates. You have to explicitly define your state variables, write out the loop, and dictate exactly when that loop stops. The imperative approach maps perfectly to how the physical machine actually transitions between states, but it absolutely forces the programmer to think like a machine.
And this brings us to a fundamental law of computing. We sacrifice the conversational ease of natural language for bit-perfect, deterministic execution. This is exactly why your whole program crashes if you miss a single semicolon in C++, or if your indentation is off by one space in Python. That strict, totally unforgiving syntax, that's the necessary price we pay for predictable, auditable performance. The physical hardware can't guess what you meant. It can only execute the exact state changes you dictate.
Finally, Section 5, the compiled AI solution. Let's see what happens when modern AI collides head-on with this rigid hardware.
Right now, we're increasingly asking large language models to act as natural language compilers. But remember, natural language is inherently ambiguous. If you miss a comma in an English sentence, people still know what you mean. But if an AI makes a probabilistic guess and writes code missing a semicolon, the whole system goes down. If an AI tries to map fuzzy human speech directly into that unforgiving syntax space, we risk losing deterministic engineering completely. Relying purely on AI generation leads to what developers are jokingly but accurately calling prompt and pray development. And honestly, that is incredibly dangerous and nearly impossible to audit for security.
To fix this, researchers are building some really fascinating hybrid architectures. A great example of this is the yield protocol. Instead of forcing a probabilistic AI to guess at exact mathematics, yield uses a state handoff mechanism. Basically, when the AI hits a task that requires exact arithmetic, it literally pauses its standard neural execution, it hands the state over to deterministic mechanistic circuits to do the precise math, and then passes the result back to the natural language layer. It perfectly mimics the separation of concerns we see in physical processors.
And the results of this approach are just undeniable. By forcing AI into deterministic pre-tested code templates, we don't just prevent hallucinations. We are bounding the error space. The model physically cannot hallucinate a bad database schema because it's locked into a strict template. This gives us massive verifiable efficiency gains. We're talking 57 to 84 times savings at the enterprise scale. Deterministic execution means we can audit exactly where a piece of code fails and fix it with complete precision.
So, I'll leave you with this to chew on. As AI continues to bridge this massive gap between our fuzzy, expressive natural language and the cold, exact reality of silicon states, which path is going to win out? Are we moving toward an era of highly compiled, deterministic engineering, where AI is kept strictly bounded? Or are we just going to surrender to the chaos of prompt and pray development? Understanding these physical hardware constraints and the absolute necessity of imperative, step-by-step logic might be the only way we ensure our future systems actually remain under our control. Thanks for joining me on this explainer, and keep questioning the code behind the curtain.